Welcome to Physics 1.1. This is entitled Physics is Transcendental. It says science does not know its debt to imagination, and that's a famous quote by Ralph Waldo Emerson. So the goals for this presentation are number one, that students recognize the importance and apply the rules of proper measurement, that you be able to convert between systems, that you be able to understand and apply scientific notation, and finally that you be able to manipulate algebraic formulas. So here's what we know. We know for middle school that we can measure the length of or between various objects. So I can say, here's this, here's an object here, here's an object here. I can measure the distance between them, or I can take this object right here and I can measure the length of it. You also know that occasionally there's a relationship between measurements of length. So this is a famous formula from geometry. It's Pythagorean theorem. A squared plus b squared equals c squared. So there can be a relationship between two measurements. Now, in the lab you learned that there was definitely a relationship between the circumference and the diameter. In fact, whenever you graphed it with the circumference, or excuse me, the diameter on the x-axis and the circumference on the y, you actually got a slope of 3.1415. Now, you may not have exactly gotten 3.1415, but you should have been somewhere close to that. Now, whenever you do that, you have an equation that defines this as the circumference is equal to 3.1415 times the diameter. And you should recognize that as the same one from geometry, that's c equals pi d. So the point of this lab was to show you that every equation that you've learned in algebra and geometry has an experimental or an empirical relationship that describes it. It's not like somebody just said, hey, let's make this equation work. So, crazy equations. Algebra is useful for representing the relationship between variables. Physics equations allow us to examine those relationships, so a lot of you look at it and go, wow, that looks ridiculous. Why would anybody ever write something in this form? And the reason is, it actually makes your life much easier. You're able to keep track of the terms a lot better. You're able to move things around more clearly. You're not likely to make mistakes when it's in this particular form. And also, these equations represent general rules so that you don't have to redo every single experiment for every single situation, because you know this rule will apply. So let's rearrange things part one. So we have an equation right here. This is one of the equations you'll be using in physics this year. It says A equals VF squared minus VI squared divided by delta D. First things first, these variables represent different things. This VF represents one variable. You have a variable V with a subscript f. That subscript is used to define the variable. It's not used to say two different variables, but it says, this one in fact stands for final velocity. So the variable is velocity and the final is the description. You see it again right here with the I. The I stands for initial in this case. So whenever you see a subscript, that subscript is just used to define the original variable. Also, you know delta. Delta stands for change. So this right here is the displacement. Delta D is one variable. Okay, delta D is one variable, just like VF was one variable. If you ever have a delta in front, the delta represents the change in the subsequent variable. So in this one, now we need to do is we need to say the variable of interest must always be in the numerator. So I want to rearrange this equation right here for delta D. The problem is that this delta D is in the denominator. So the first thing that I want to do is I want to multiply both sides by delta D. Now when I do that, I have delta D on the top and delta D on the bottom, but those things cross out, and it makes it much simpler. But remember, what you do to one side of the equation, you have to do to the other. So I multiplied this side by delta D, so I must multiply this side by delta D, and that's why it's there. Okay, the next thing that I need to do is I need to continue to isolate my variable of interest. So if you were to look right here, once I've done this, I've got this delta D, but I want delta D by itself. I don't want it multiplied by A. So I divide both sides by A, and that cancels the A's out. But what I do to one side, I have to do to the other. So now this one now represents my variable of interest. So this is the rearranged version of this particular equation. You should have gotten a lot of practice with this in Algebra 1, but maybe not using the same types of variables. You may be used to using x's and y's. But the variables that we use in physics all stand for specific things. It's not a general unknown like x. It's delta D stands for displacement. A stands for acceleration. So it's really important that you be able to manipulate algebraic equations. Now this is a formula that was on the chemistry star exam. You should be able to rearrange it to isolate mass. So what we want to do is we want to realize we want to circle our variable of interest and say, okay, that's really what I want. In order to get rid of everything else, I've got a delta V on the bottom. So you always have to choose the opposite function. If mass is divided by V, I need to do the opposite of dividing by V, which in our case is multiplying by V. When I multiply by V, I have a V on the top and a V on the bottom, and those two terms cancel out. But what I do to one side of the equation, I must do to the other side. So I have my rearranged version, which is m equals dv, or mass is equal to the density times the volume. Next, we see another similar equation to the one that we just saw before. It says A equals VF minus VI over delta T. So let's rearrange this to isolate for VF. So this is really important. You got to do order of operation. If I were to add VI to both sides at this point, remember that this VI is divided by T. So you can't just add VI to both sides. Instead, you have to look at it in terms of order of operation. The very first thing that I want to do is I want to multiply both sides by delta T. In doing so, I can cross out this T with the bottom. But what I do to one side, I have to do to the other. So now I would have delta TA and then VF minus VI. The next thing that I need to do is I need to continue to isolate for VF. If I have VF minus VI, well, if I add VI, that will cancel out to be 0. But what I do to one side, I need to do to the other. So you end up with this. The more common version of this equation is VF equals VI plus A delta T, which is the same thing. VI plus, instead of delta TA, it's usually written as A delta T. So you need to remember that that delta T stands for one variable, not two separate variables. In this last mastery level question, we need to rearrange to solve for D. Once again, you can recognize that this G is a subscript of the F, so it's part of the F variable. And you see these 1 and 2 are also subscripts, so they're part of the M variables. Now this is a squared term because it's a superscript, not a subscript, so just be aware of that. So the first thing that we want to do is we want to recognize the fact that our variable of interest is in the denominator. Because our variable of interest is in the denominator, we need to go ahead and find a way to get it to the numerator, and we can do that by multiplying both sides by d squared. When we multiply both sides by d squared, that cancels it out on the one side, and we're just left with d squared times f sub g equals g m1 m2. So now the next step that we need to do is we need to divide both sides by fg. And that allows us to continue to isolate the variable d. And in doing so, we cancel that out. Now a lot of people will stop there and say, now I've isolated d, but you really haven't isolated d at this point. All you've isolated is d squared. So the last step is to take the square root of both sides. And when you do that, you end up getting d is equal to the square root of g m1 m2 over fg. Length is a measure of distance and displacement. So distance and displacement are different, and we're going to get into that in the next unit. But length is a fundamental unit of measure and is the distance or the length between any 2 points. The standard unit is the meter, and it's currently defined by how far light travels in 299,972,458th of a second. Originally it was defined in terms of a standard meter bar, but that didn't have the precision that was required, so they've gradually changed the definition to this particular definition. Time is another fundamental unit of measure. It is the interval between two events. Its standard unit is the second, and the second is defined as the amount of time it takes for 9,192,631,770 vibrations of a cesium-133 atom. Okay, that's the atomic clock. So once again, it started out with a different definition in terms of the Earth going around the Sun, but that didn't have the degree of precision that was required. Mass is another fundamental unit of measure. It is the amount of matter in an object. The standard unit is the kilogram, and it is defined by the standard kilogram. Now this is one of the things that is actually, there's discussion about changing the definition of mass instead of basing it on a standard kilogram, but basing it on something that is a little bit more standard, like the mass of a hydrogen atom or something along those lines. Temperature is another fundamental unit of measure. It is the average molecular motion of a particle. The standard unit is in Kelvin, and it's defined by the point at which all molecular motion ceases and the triple point of water. Those are the two major points that allow us to define temperature. Okay, in developing B1, it says what is the length of the scissors that is shown, and if you see there are lines here to kind of help you visualize it, but it goes to about 69.1 centimeters, and then right there you've got about 55.3 centimeters. So 69.1 centimeters minus 55.3 centimeters, and that allows you to determine what the length of the scissors is. So at this point you would just subtract, or you would get a calculator, and when you do that you end up with 13.8 centimeters. Next it says what is the volume of this particular object. So one of the things that you need to do is first realize that this is a cube. It's actually a Rubik's Cube. And if you see, you have exactly 1.5 inches, or excuse me, not 1.5 inches, 2.5 inches is the length of one side. Now, the reason why I know it's inches is because of the way the markings are on the ruler. You wouldn't exactly know unless you were the one making the measurement. But if each side of a cube is 2.5 inches, now you would have to use a formula that you learned in geometry, and that is that the volume of the cube is equal to s cubed. So you would take 2.5 and you would cube it, and then you would have your answer, and the unit would actually be in inches cubed. So I'll let you go ahead and put 2.5 and then cube it in your calculator so you can get used to entering calculations. The last one we have is what is the volume of the object shown below? This is a cylinder, so you have to do the formula for a cylinder. The formula for a cylinder is pi r squared h. That represents the formula for, or the volume of a cylinder. So if you look, you have the height of a cylinder as 2 meters. That's relatively easy. You would plug it in there as 2 meters. Okay, right here, this does not represent the radius. You would have to make the radius 1.5, or half the diameter. So at this point, you would plug in 1.5 and then square it. Okay, at this point, you would be able to plug it into your calculator and calculate the volume of this particular object. Now, the units would be in meters cubed. The reason why is you have 1.5 meters, and that's squared, and then you're multiplying it by meters again, so it makes it cubic meters. And you should put that in your calculator and find the value. But units don't really matter, right? Well, a lot of people they tend to get points taken off in this class, and the reason for that is they leave the units off. Units really are significant in physics because there's a big difference between 10 kilograms and 10 milligrams, or between 26 meters per second and 26 miles per hour. They're very, very different. So here's an example. This is the Mars Climate Orbiter. It cost about $330 million to make. It used the ground software used the English system of measurement. The onboard software uses the metric system of measurement. And as a result of this inability to convert between the two systems, the craft was lost with all material, instruments, and data aboard. Once again, $330 million because somebody didn't convert. So why convert? Measurement cannot always be done in standard unit. For example, whenever we measured the circumference and diameter of the different objects that you measured in the lab, we couldn't exactly measure it in meters. Now, we could express it in meters by converting it after centimeters into meters. A lot of times fundamental constants are required, and they require calculations in standard units. So that's the reason why we need to convert, and why we need to convert before we do any calculations. Okay, so here are some common English conversions to metric. 1 inch is about 2.54 centimeters. You're going to use that one a bit. This is the most common one that you'll use, that there are 1,609 meters in 1 mile. Okay, that's why you run around the track 4 laps before you get to a mile. You will also use this one, that the mass is 2.2 pounds is 1 kilogram, and you should know that 1 hour is 3,600 seconds. When we get to temperature conversions, when we talk about thermodynamics, we'll go over the temperature conversion again. So, metric conversion factors. It is important that you be able to memorize and apply these particular prefix relationship units. So, if you were to look at this, 1 gigameter would be 1 times 10 to the 9th meters. 2 megaseconds would be 2 times 10 to the 6th seconds. 5 kilograms would be 5 times 10 to the third grams. So what you see right here is these are the conversion factors to the base unit. The base units are seconds, grams, meters, those sorts of things. You may see a few more like amperes or volts later on, but they're the standard units of measure. And in fact, these are the base units that we're talking about. Okay, so 2 mega amperes would be 2 times 10 to the 6 amperes. So we're going to do a calculation here. It says determine the distance in standard metric units of 26.2 of a marathon, 26.2 miles. So we have 26.2 miles, and we're going to use dimensional analysis in order to do our conversion. We know that 1 mile is 1,609 meters. When I do that, this is done, and I can say miles cancels with miles, leaving only meters. When I multiply these two things together, that will give me my answer. You need to get used to using your calculator, so go ahead and plug that into your calculator and determine your answer. Proficient. It says a weightlifter is capable of bench pressing 250 pounds. What is the mass in standard metric units? The reason why this is a proficient level question is a lot of times people think that the gram is the standard unit of measurement. It is not. It is the kilogram. It is one of the standard units of measure that is not a base unit. So we have to convert 250 pounds. There are 2.2 pounds in 1 kilogram. Okay, pounds cancels with pounds, and we're left with only kilograms as our answer. And now we would take 250, multiply it by 1, and after we multiply it by 1, we would divide by 2.2, and you should get your answer, which is somewhere over 100 kilograms, but I'm going to go ahead and let you do that in your calculator. The next one says a car travels 80 miles per hour down the highway. How fast is this in standard metric units? So you have 80, and this is where it's a little tricky. You have miles, and then the per means divided by. So you have divided by 1 hour. Okay, so when you have 80 miles per hour down the highway, how fast is this in standard metric units? Well, the first thing you need to realize is that hours is not in standard metric units. So if that's not in standard metric units, the first thing that you're going to do is convert 1 hour into 3,600 seconds. Okay, but you're not done. You've canceled hours out, but if you were to stop at this point, your answer would be in miles per second, and that's not what you're looking for. So the next step is to go ahead and say, okay, well in 1 mile, there are 1,609 meters. Okay, miles cancels with miles, and you would do 80 times 1 times 1609, and that would be the numerator of your function. Now the next thing you would have is 1 times 3600 times 1, which is 3600, which is the denominator. So in your calculator you would do 80 times 1 times 1609 divided by 3600. I'll go ahead and let you get practice by putting that in the calculator, but your answer is going to be in meters per second. You also need to know how to do scientific notation. Scientific notation is the process in which you take large or small numbers and make them more reasonable to work with. So right here you see that the Earth has a mass of 59800, and there's a whole bunch of zeros, kilograms. Well, the mass of an electron is 0.00, and there's a whole bunch of zeros and then 911 kilograms. So whenever you're trying to deal with numbers very large or very small, that's when scientific notation comes into play. Scientific notation, the number m, okay, that represents m, must be a number between 1 and 10. It can be 1, and it can be 1.1, and it can be 5, and it can be 9, and it can be 9.99, but it has to be a number between 1 and 10. It cannot be 10. If it's 10, you would put it as 1. If, for example, if the number that you're trying to put in scientific notation was the number 10, that would be the number 1 times 10 to the first. Okay, this first term must be a number that's 1 or greater, but has to be less than 10. The second number, this n value, is the integer. It's the number of places you have to move the decimal place to make the number between 1 and 10. So for example, the one that we gave before, I have the number 10. In order to get it to be 1.0, I had to move the decimal place over 1, and in doing so, I made it times 10 to the first because I had to move the decimal over one place. Your physics teacher tells you that your grade is a 9.6 times 10 to the 0. What is your grade in standard notation? Well, 9.6 times 10 to the 0. This tells me that I'm not going to move the places over there. I'm not going to move it over any places. So your grade is a 9.6, which is relatively difficult to do. Next, we have an astronomical unit is the distance between the sun and the earth, which is 150,000,000,000 meters. Express this in scientific notation. So here's the decimal. For each comma, I'm moving it over 3. So 3, 6, 9, 10, 11. So now I can express it as 1.5 times 10, and it's a really large number, so it's a positive 11. The last example we have, it says a cesium-133 atom vibrates 919263177 times in 1 second. Determine the time of a single vibration in scientific notation. So this one's actually kind of tricky because this is saying you have 919263177 vibrations per 1 second. And you want to know what the time is per one vibration. So you actually need to flip these things. It should actually be 1 second divided by that. When you do that, you end up getting a very, 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 very small number. Okay, the number that you end up getting is a decimal that is 0.00000 and then a number. Okay, there's a whole bunch of zeros there. So now what you need to do is you need to count the number of places that you need to move the decimal. Once you've done that, realize that your original number was a small number, so you're going to have times 10 to the negative. Now I'm going to have you guys get some practice by putting that in your calculator, but realize that it should be times 10 and it should be a negative value because it's a very, very small decimal to begin with.